Hi everyone. So today we'll have the fifth lecture of our Causality series. Today we'll be speaking about TarNets, continuation of the proof and so on, and we'll speak about if time permits, we'll also introduce causality.
Yeah, okay. So again, recap for people who may have missed previous lecture. So we were talking about the individual treatment effect, and we said under ignorability and positivity and consistency, again, the three conditions. This was actually equal to the conditional average treatment effect, right? Which was just simply the expected value of y1 conditioned on t is equal to 0, x or 1, right? This is a difficult thing to estimate. But then again, we basically said this is just nothing but the expected value of y1 conditioned on t is equal to 1 comma x, essentially reducing it to a regression problem, right? And then we discussed three estimators, basically falling under the rubric of meta learners, right? So one is to say you try to condition on t and estimate two regressions, and then you take the difference. That's called the t learner. The S learner is consider this to be one regression problem and regress on t comma x, get what is called the S learner. And the more interesting one was the X learner, which is you first take the regression outputs for either one of those learners, let's say t learner, and then you want to estimate the treatment effect, right? So you want to take the difference, but the difference could have a simpler dependence on x compared to each one of the response functions. So the question was, from a finite sample complexity point of view, can you exploit that? So what we basically showed was that here you could sample complexity of the form 1 by m power a plus 1 over n, where n is the number of treated variables or the treated samples. This is the number of untreated people. And technically, usually, this is much greater than the treated one. So you could try to estimate the regression only for one of the groups, where the parametric rate is not achievable. A is usually less than 1, which means 1 over n is not possible. So the error doesn't go as 1 over n, like in least squares linear regression. Maybe it's a very complicated regression class, so it actually goes at a much lower rate. But turns out, if you use this composite X learner, which is to first estimate the response function, create the difference, and then second one using a linear function, we basically showed that you can get the best of both in some sense, right? So if you use the t learner, your samples should have been 1 over m power a plus 1 over n power a, which is basically a regression cost for both the groups. Okay. So this also showed how regression from one group can be translated to another group, and then you can try to actually do a treatment effect estimation, right? So we proved all this last time. Okay. So this X learner is not just about some intuitive idea that you can come up with. Of course, you can do mix and match regressions in any way you want, provided that this is what you want to estimate. But turns out there is a sample complexity advantage, right? So this was from the paper, meta learner paper that I cited. So then today we are going to talk about TarNet. I introduced the architecture last time. This goes into borrowing ideas from domain adaptation and using it for individual treatment effect estimation, right? So that's the basic thing. So let's get started with this, and there's a proof here to show that this method has some nice sample complexity or error bound behavior. So I can actually show you that. So let's get started with TarNet. So the question is, can I write here, or do you want me to write there? No, it's okay. I can just erase the recap. Okay, what was TarNet? Okay, remember, whenever you're trying to estimate the y1, right, you always use the treated sample to do the regression, right? So in practice, you will have a club. So we know that positivity holds. So P of T given X is always positive for all T and for all X. So we always operate under this assumption. However, we only have finite samples, right? So if I want to estimate the expected value of Y1 given X, was very typical with respect to the untreated population. So basically what I'm trying to say is you have one cloud that looks like this. You have another cloud that looks like this. This is T is equal to 0. This T is equal to 1. I'm trying to understand what would be the treatment, like what would be the potential outcome if you were treated, but for T is equal to 0 population, right? So potentially I would see, if I have n tends to, if I have infinite samples, clearly you can get a good estimate of this. I'm not going to argue about that. For every X in the domain, you're fine. But in finite samples, the main issue is that you could actually get a point over here. And the only thing you can do is you can find a point closest to this, but not exactly here, right? So when you try to do regression based on the treated population, this is basically an extrapolation, right? And you have to live with it. Okay. So the question is, can you actually do something to ameliorate this issue? That was the main reason behind TarNet. Okay. By the way, in machine learning, you have analogous problems where you will have targets for one population, but the test distribution does not have any labels. Assuming the conditional distribution doesn't change, can you actually predict for the new samples that you have not seen? So this is a very typical problem that people use in unsupervised domain adaptation. So there was a recent set of works since neural nets became very popular. Yes.
So doesn't our ignorability condition let us get away with this by saying that, okay,
it'll only get away. So this is the only thing you have, which is an expectation, right? So when you have infinite samples, yeah, you are fine. There's no issue. You can do X learner, T learner, one of them, everything is consistent. So we are not bothered about that. The question is for finite samples, you still have an extrapolation problem. In reality, you will have an extrapolation problem. But can you do something to ameliorate this? That's what I'm trying to understand. Is there any other question? Okay. So why is this even possible? Why do we think it's even possible? Right? So let's go to the ignorability criterion, which is this is positivity. Again, let's go back to the same criterion we've been discussing for almost 4 lectures now, which is y1 is y1 comma y0 is independent out of p given x. Right? Now, suppose so the main problem is you have p of x given t is equal to 0. This is not equal to p of x given t is equal to 1. Right? So they're just cube distributions. They look like this. Not to say that this point is not this point doesn't have positive probability with respect to this distribution. It's just that in finite examples you didn't find anything here. Right? So what I could do is that I could map x using a transformation phi to some range space R, right, where phi is 1 to 1. And therefore, for the image of x with respect to phi, I can always come back. I can always invert only from the image, right? So R is basically the image of the domain under phi, right? So this is my definition. So this is the source domain from which x is drawn, right? And I have map 1-to-1 map from x to R. So if I have any target point here, I can always come back uniquely to this because it's a 1-to-1 map. Right? Now, suppose I do a clever, I come up with a clever phi such that the probability of phi of x given t is equal to 0 is exactly equal to phi of x given t is equal to 1. I'm not saying it can happen. I'm merely saying that suppose I could do this, right? Then you're still fine. Why? Because ignorability due to 1-to-1 nature of p actually implies ignorability on P also. This is possible, right? Yeah.
Should that be P X to R? And it can be X to RD or?
Yeah. What I meant was such. So P is a function from X to R. P is 1 to 1, which means over this particular range, it is invertible, right? So there's no information that is lost from X. You told me that the information in X will make sure there is no effective confounding. That's what.
And you don't mean R for range, not for real, right? Or
Yeah, R is for range. I mean, it's.
It can be any RD.
Yeah. Maybe calligraphics. I mean, I just used it for the word range,
yes.
But I didn't mean R or R to the D or anything. So because P is 1 to 1, right? Conditioning on X is same as conditioning on P of X, right? So what have I done through this transformation? I have essentially solved your problem of mismatch, which means I've almost made it a randomized control trial, right? But then I've retained ignorability, right? Then you no more have this problem. Basically, the clouds will sort of become they'll overlap. There is no extrapolation issue to be found. Right? Yes.
Just to confirm, so here X is a continuous random, not discrete like I think.
Yeah, X is a continuous time.
X is that is the density over.
Yes. Yes, this is the density function. See, I am. See, if I can go to measure theory, I can go to random negative derivatives, I can put all that stuff on you. The point is, easiest understanding is that there's just a density function, right? And this is also a density function with respect to field. So the main point here is, if it's a one-to-one transformation, and if I could get it, I mean, you can't get it to be equal if the original thing was not. But what I'm trying to say is that if you can get it closer, right, then you will ameliorate a bunch of these problems. And we are going to formalize this. And there's an architecture which actually does that. And it directly borrows from unsupervised domain adaptation. So one of the important open problems is the following. If I don't have one-to-one, I'm trying to match it. Whatever I'm going to say is not going to hold. Because you've destroyed ignorability. And the moment you've destroyed ignorability, this regression does not have any more significance about estimating the potential outcome. So the more important general open question is, what sort of transformations can you come up with such that, let's say this is balanced, but you still can do this type of regression? Under what conditions can you actually do that? So when I ask this question, it may not be very obvious to you because the only thing I've discussed about is ignorability. So I'm really asking for what all fees this is satisfied. Clearly, if it's one-to-one, it is satisfied. But turns out that if you go to Perlian frameworks, you can say something more. Even if X does not satisfy ignorability, you can find conditions on phi such that phi can satisfy, which is actually the real problem in Simpson's paradox. I will always give you an X most likely that does not satisfy ignorability, because if it does, maybe you can do other things too. Right? And I'm looking for a transformation such that it becomes mostly ignorable. Plus, it also has some good balance. Okay, there's a lot of open questions around how to actually achieve both. You give up on one. You just say, I only restrict myself to one-to-one transformations. And therefore, there's only so much maneuvering you can do. But then you try to match the best of your ability. And then you basically use that to do regression.
I mean, as you said, like if it's so hard to imagine that if X does, so I mean, somewhat abstractly, what is happening that you have these two conditional distributions on X which do not match.
Correct.
I mean, let's just, for the sake of my understanding, think of X as a simple real, like a real random derivative. Now, T of X would be like you apply some function to it.
Correct.
But I don't see that you can get exact equality.
No, you can't get exact equality. You'll be close. So I just said that suppose you could, then if P was invertible, then you're fine. I'm not claiming these two hold if this is not true. I'm not making any illogical claim. All I'm trying to say is that you would ideally like this if P was invertible, and if originally X satisfied ignorability, you could get this. The open problem I'm talking about is the following. In a very general problem that X does not satisfy ignorability,
you do is very suggestive. That is, especially in the case where like there's no probability in the like set difference. In the intersection, you let P of
Yeah.
be X, and otherwise make it something equal.
Yeah, you could do all such things. Yes, true.
And is there a notion of so I mean, going back to the open question that you're posing, is there a sense that I don't need exact equality, but an approximation would suffice?
So that's what we're going to prove. That's already sort of done under this condition, the phi is 1 to 1. But I'm asking a more general question. We always started with an x that is ignorable. But in reality, you are not going to be given an x that's ignorable. But you can define a space of transformations. Right? Now, what if x does not satisfy ignorable, what sort of phi will satisfy ignorability? This is question 1. So there has been some recent work that tries to answer this question. Okay, but the full picture is not clear. Like when all can you assure ignorability under what are conditions you can do that? It's absolutely not clear, right? There are lots of assumptions, other assumptions you have to make in order to basically constrain phi such that this will actually satisfy ignorability. A bigger question is, can you get both? Like, can you have a phi that results in ignorability and that also results in good matching? Right? And how do you actually do it?
You mean this?
Yes. I don't mean exact equality, I mean coming close to each other. So can you actually do that? Right? Under what conditions?
Sorry if I missed it, but why do you need phi to be 1, 1? Can I ask for phi to be 1, 1 in that overlap space rather than
I want phi to be 1, 1 because without this, I can't go from counterfactuals to regression. That's my only problem. So with whatever I've told you so far, the only vehicle that you know is ignorability, and you don't want to dispose that up because otherwise there is no way this is true. So this depends on ignorability. Right? And this is not true with respect to phi. You can't go from here to here. I mean, this is still legitimate. You can have expectation of y1 given phi of x. That's all very, very nice. The only problem is I can't actually have any way of estimating, at least even in the middle. So you don't want to destroy this property. Right? But I'm asking more broader questions. I'm saying that there's a lot of open questions where x may not satisfy ignorability, but there's a transformation phi, but that can actually satisfy ignorability. Okay. Now, the reason I said this thing is that when phi actually selects features suitably, I haven't told you how to select features yet, then this is implied, I mean, how to do that very well is actually implied by Perlian models. This is one of the main motivations, at least classically, to study Perlian models. So here what I've said is if x is ignorable, if I have a one-to-one function, I can do whatever I want. But suppose that's not even satisfied. So I'm actually departing from all the things I said in the first 4 lectures. This is a good place to discuss the departure. So it will motivate very well what I'm going to say from this lecture and or maybe the next lecture. So if I have x that is not ignorable, when all can you find a phi such that it becomes ignorable? Right? A subset of these questions has been answered in the Perl. Right? Yes.
So 1-1 condition is just like a sufficient condition.
It's a sufficient condition. So if you want the most general set of conditions, you need to assume something in causality works without assumptions. So if you assume a causal Bayesian network for energy, then you can answer this question a bit more generally. But the question is, how much assumptions do you need to impose earlier models before you can actually certify a phi? That's really the question. So can you make this as minimal as possible? You come up with like design procedures for phi such that this is true. This is a very big question. So the Perlian answer currently, that is the conventional one, is that you tell me a lot about how the different features of x interact with each other in a causal graph. If you gave me that, then I can answer this question for you by doing an appropriate feature selection. But then the question could be more broader. Okay, I can give you some information, but everything else you just do whatever you want to do. I just give you the data, you just figure out a few. So how do you actually do it more generally? This is a very big open question. Right? So how less you want to assume about the causal model, without directly assuming ignorability, of course. Then the question is, can you actually design a fee such that it's ignorable? So that's the main question. The second question is, can you actually achieve both? Even a deeper question. And a lot of people have not studied this that much. I mean, there are nice papers follow-up of TarNet. They try to solve some issues there, but it's largely an open question.
We not need positivity to also hold.
Yeah, I'm saying even if positivity holds, I am trying to say that unless we is one-to-one, you're not going to get, because the main bottleneck is not positivity here. The main bottleneck is that in order to go from here, potential outcome to actually observable variables, you also need ignorability. I'm saying all this under positivity. Without positivity, I don't think you can do anything.
Positivity under P of X. So
Yes.
need P given P of X also.
Yes, but that's sort of implied here, right? If they are equal, then if they are close to equal, then yeah, it will happen.
Like I'm just thinking of a trivial, not a trivial, but one way to go about what the second point is that I do the feature selection using the Perlian deseparation, whatever. And then I just now try to have another mapping from that to.
Yes, you can do these compositions and all that. But what's the general way of doing? But in order to do that Boolean feature selection, you need assumptions about the model, right? So I want to ask minimal assumption about the model, and I want to reach to. So the question is, what's the space of assumptions you can make, and what's the trade-off that you can get? People have explored, but I'm not saying that this is like a well understood.
Without graphs, have people looked at one like other assumption?
Yes. So I have some more recent work on that. There are other people who are looking into those things. Yes, there are some work, but whether the conditions are general enough, do we understand under all conditions when you can do it, when you can do it? I don't think so. Because the Perlian thing is if and only if. If you assume that data was generated according to a causal Bayesian network, there are some feeds that exist, or in some cases, depending on the graph, no feeds. Okay, I can give you a certificate. I can tell you very clearly, and that's called the identifiability problem. But when you start reducing assumptions, not very clear, like what is necessary, what is sufficient, can you find? I mean, all those things are sort of open.
Just to go through, like, let's assume we have such a P one-to-one and like gives us this box equality. It helps our life because now if I apply phi and then try to do the regression, the problem.
I'm going to do an error bound.
Okay.
That's precisely what I'm. So I'll erase that part, right? That was just motivation to what is to come. It's a good place to motivate the Perlian models. This is one of the prime reasons why you want to study Perlian models, but there are much broader reasons. And I'll come to that. Yes.
The set of all fees is very large, and you asked for one condition that is one. So between all of those functions, how do we choose?
Yeah. So in practice, so I'm going to draw how TarNet is achieved in practice. So it's just a neural net. Whether we can ensure all of these things or not is it's a question. Yes.
How do you solve that condition?
Because the distribution of treated people and untreated people are in general different. If I could match them in some statistical distance, then essentially I get better and better results, which is exactly what I'm going to prove under one-to-one.
Instead of independence in ignorability, you can have an epsilon independence.
Okay. Okay.
Those things make sense.
Yes. So there's a whole field called sensitivity analysis, where what they do is that they say the mutual information here is less than epsilon in some suitable way. There are many ways of imposing this constraint. So there are some antecedent sufficient conditions that imply what you're saying. Under that, you cannot estimate the effect, but you can get a bound, even in the infinite sample. You can say the effect lies between blah and blah.
Right. So those two things will not be equal, but they will be.
Yes, you will be upper bounded by something and lower bounded by something. And depending on how you make this assumption of mutual information being less than epsilon, you can actually give parametric bounds, non-parametric bounds sometimes.
Then, like finding a which is approximately, which satisfies approximately
That would be, yeah, yes, both approximate would be probably. But the question is, forget about how you find it. Let's say you have optimization problems which if you solve in some infinite limit, you can prove that you can find it. That's still fine. Question is, how do you prove bounds? Like finally, I want counterfactual loss. So what is the loss going to be bounded by? So one such analysis for this very strict condition, I'm going to talk about today. The generalization of this, a lot of it is open. That's all. Okay, so let's go to TarNet architecture. So it'll become more clear. I hope the objective is clear at least. Right. Okay, so the TarNet architecture works as follows.
Mathematically, it's this, right? Like you have one random variable, like you have a joint distribution, and you want to match like transform X such that the conditional distributions are as given. That is the abstract.
But what is why conditional? I mean, you have two distributions.
You have X and T, which are a joint distribution.
Ah.
And you're looking at this conditional distribution, which is P of X given T equal to 0 and P of X.
Yes, I want them to be correct.
Yeah. That is like, mathematically.
Mathematically.
That is the problem.
So let me actually draw the architecture. This was in this paper. We should quote the paper here before I start. So it's called estimating individual treatment effects. I think through covariate balancing or something, I don't remember, but the author names, so it's this 2017 paper, ICML, I think. And the author names is Sontag, Urishali, and Johansson. By the way, I don't remember the order, right? I just know the author names. This is a very, very important paper in ITE. This sort of spawned a lot of work on how to adapt neural architectures to actually solve the ITE problem. But the key issues are these two. How do you, like you said, how do you get approximate ignorability? And how do you get matching? But always the assumptions are whatever features you have given are already ignored. And the only thing you're doing is trading off one with the other. That's what you usually think about. But the questions are more general. If Perlian model says that under sometimes you can actually construct phi such that even if X is not ignorable, phi of X will be ignorable, it means the thing is not fully solved. Right? So there's a little bit more to think about. Yes.
Sorry, but going back to probably a stupid question, but coming to this picture, we are thinking of it as support, but let's think of it as two distribution.
Okay.
Take any one point on, let's say, the overlap.
Mm-hmm.
Like the probability of y given t equal to 0 is going to be different from y given t equal to 1.
Not y. This is X.
Yeah.
This is the X space.
Sure. Okay. Probability of x given t equal to 0 is different from t.
Yeah, the density function is different. Yes.
After you transform it, it will still be different.
But it might come closer, right?
But point-wise, it will be different. I see. So the problem is point-wise, it will be different, but somehow density-wise, you want it to.
See, I mean, there is a theorem that says that you take a uniform distribution, right? You can transform this to any continuous density you want, right? Using the inverse area of transform. You can invert it. True, right? Because it used to be monotonic average. So clearly, if I give you two distributions, I can find two different functions that can actually come back to the same density function. That much is very clear. The only question is, can I find one transformation such that they come closer to some target distribution? It could be potentially achieved. I'm not saying equality is achieved. I'm saying it can be brought closer. And I'm going to derive a soft version of the error bound. Like depending on the distance, we are going to basically say the error actually scales with respect to the distance. Okay, but now I have to define a ton of things. So before that, let me actually give you what the architecture is. Maybe you're not interested in the neural net architecture per se, but I think it's good to have it. Then I'll prove if certain nice things happen with respect to the architecture, like phi is 1-to-1, etc., etc. I'll actually show you how closeness here helps. Okay. Now you take X, you transform using this some neural net phi, you get phi of X, right? Then you take the treatment.
So right now we're already looking at closeness in a probabilistic sense.
I will define in what sense.
Okay.
I have not done anything, but the moment I go to the proof, I have to first tell you in what metric am I actually considering closeness. It will be some integral probability metric. I'll introduce what integral probability metrics are. The simplest example is Wasserstein 1. Okay. But I'm not going to go into how Wasserstein 1 has multiple ways of writing things and all that. I'm just going to define it in one way and just proceed. And then I'm going to tell you how if it's closed in that, like epsilon closed in that with respect to matching, but ignorability is perfectly satisfied, how the errors are related. Counterfactual error and factual error. Because factual error, the only thing I have said is to the treated people, you can do regression. And untreated people, you can do regression. This will be Y1's estimate, that will be Y0's estimate, but they are on slightly disjoint supports. So all I can do is relate the counterfactual error to the factual errors, plus something. So I'm going to talk about that, what that plus is. Okay, yeah. So let me fully finish the architecture and then I'll definitely do the proof. So that's what today is for. So now what you do is you sort of split it into two, t is equal to 0 and t is equal to 1, right? And you have another neural net, which is H1, which tries to predict H0, tries to predict Y0. And this is H1, which actually tries to predict Y hat, right? But what do I need? I want to make sure that these two are also very close in some integral probability metric. There's an IPM loss. I'll talk about what this loss means. Basically, it is trying to make sure that some distance function between P phi of t is equal to 0 and P phi of t is equal to 1 gets smaller. Okay, so this is all regression loss. So the way you train this network is you do y minus h0 composed with phi for all the untreated people. Then you regress y on h1 composed with phi of x for all the treated people, right? And you basically have some least squares loss over here. Then you simultaneously make sure that the phi of x that was split based on the treatment or the status of whether it being controlled or treated, some metric, some distance, a probabilistic distance actually goes down. This is the architecture. So the final loss function is basically some regression loss between y and x with respect to the treated population, the untreated population. Again, a regression loss with respect to y and x for the untreated population, plus this IPM metric between p is equal to 0 and p is equal to 1. So this is the general loss function. You can realize it using MMD metric. You can realize it using Wasserstein and so on. And I'm going to what those things are. Okay. Right? I've not fully specified what the thing looks like. I have to still specify what the distance functions. So I'm going to go there.
Regularizer y equal to 0 to p of x, right?
Yeah, p of x. Yeah, I mean, yes. There's the three loss functions. It's not very important how you achieve this. What's more important is if you achieve this, how is your counterfactual loss going to be bounded? That's the more important part.
This summary is that you're trying to minimize three things simultaneously. One is that with respect to P, I have good regression, both in the treated and untreated population, and the matching, as you said, is.
That's it. Now I'm going to show counterfactual loss is bounded by these three quantities. That's going to be the proof with some constants in front. Before that, I need to tell you a little bit about IPM metrics. I know it's a CS audience, so we're going to define a class of distance functions between distributions. So you're not familiar with it, then this is one way of defining it. But it's not the divergence way of defining it. It's a very different way of defining it. So let me actually do it. So let me erase here. Okay. They're called integral probability metric. The reason we study them is because even in finite samples, sometimes you can non-parametrically estimate them up to some reasonable accuracy. That's the only reason we are even studying. And these are very, very related to discriminators in GANs also. So the computational part that you usually use for discriminators in GANs, a small variance of them, like specific versions of them, is what we are going to use here. Okay. So before that, so if you have a distribution P1 and you get some samples from here, and you have another distribution and you get samples from here, right? Now you have n samples here and n samples here, let's say, and you want to actually define a distance measure between them. Right? That's really what. So there are several distance measures, obviously. Total variation distance is one. Okay. So total variation distance is one. Of course, there's scale divergence, provided there's some absolute continuity between P1 and P2. We are not going to be bothered with this, so I'll just leave this comment as it is. The third sort of, in some sense, generalizes total variation distance in one way, which is called the IPM. So the idea is the following. You take a function class f, suitably defined. I have not told you what it is, but there's some function class. Now what you do is that you find the difference between expected value of f of x under P1 minus the expected value of f of x under P2. You take the difference. Okay. So any f here is called some sort of a witness function. And the witness function comes from this class. So you will say that P1 and P2 are far if I can find a witness function from this class such that it can separate them in the first one. Right? So you do soup over f is equal to f. This is basically called the integral probability metric. A very general name, depending on which function class you choose. Okay. Now, the good thing about this is that unlike K divergence, it does not require absolute continuity in general. I mean, sometimes it might, but in many cases, you don't require absolute continuity between P1 and P2. So it means it can genuinely deal with distributions which are actually not matching in support. Okay. So that's why you don't have to worry about those kinds of issues. That's why they are really good. So that's one thing. Now, what are the function classes for which some popularly known IPMs are available, right? So we'll go there. If the function class is a space of all classifiers, which is a function from x to 0, 1, then you recover total variation. Okay. I mean, they can be defined in many ways. This is one way of defining them. If I take the function class to be all functions which are Lipschitz, then you get Wasserstein 1. Okay, Wasserstein 1 has a coupling interpretation. I'm not going there. You can define the same thing using coupling, but so you define a transport cost and you consider all possible couplings between two distributions such that you minimize the transport cost. By Cantor-Ridge duality, you can show that's exactly equal to the soup of over all functions, that's Lipschitz, right? And you have this integral property. Okay. Yes.
Isn't that exactly the GAN? Wasserstein GAN.
Yes, Wasserstein GAN, they exactly do. Right. And if f comes from a reproducible kernel Hilbert space, which is basically parameterized by kernels, right? And if it's a characteristic kernel, that's very important. Then you have what is called the MMD metric, which is maximum mean discrepancy. Okay, but you have to define an RKHS space, which means you need a PSD kernel. Okay, and there are functions in the kernel space. The simplest way is it's a vector space of functions of the form k of x comma y. It's a simpler way of defining them. By the way, this doesn't capture all functions, but it is dense in L2, depending on the kernel that you use. Which basically means if you have squared integrable functions, you can arbitrarily approximate them by some member of the RHS space, right? So that means it's a good witness function. So I'm looking at all functions that are square integrable. I'm just basically saying what's the moment under each one of them, and then I'm taking the difference, and I'm basically trying to maximize, right? Now, we are not going to argue about how you estimate any one of them in examples. There's enough literature on that. For example, if you want to do Wasserstein GAN, I mean, like you said, the thing you do is you just take a neural net and make sure that the weights are scaled in the sense that the weights are restricted. So if you restrict the weights, it automatically becomes Lipschitz, right? So with the weight decay, you just try to do neural net of x expected value minus neural net of x expected value, and you just take the difference. Right? And if you do that, then you would be doing Wasserstein, right? And you could say that you might want to initialize this architecture with a discriminant. It has nice connections to GAMs also, right? So the most important thing is that the IPM choice is sort of irrelevant, right? But what we are going to actually argue is that if certain conditions holds for the loss function, then this IPM error will sort of feature in your counterfactual error. So basically, your counterfactual error will be factual error plus the IPM. That's what we are going for. There will be other terms, but that's not very important. The key thing that I'm going to prove today is counterfactual error is upper bounded by factual error plus IPM under ignorability and under one-to-one nature of P. So those are big assumptions. If you want to generalize this, the more general thing would be approximate ignorability, approximate matching. How do you bound counterfactual errors? In what all cases can you even say something? That's a very big open question. It's not so obvious answer. Right? So let's see this.
Why do we specifically use IPMs and not others like divergences?
Because if you do a transformation using phi, I have no idea where they will end up, right? So I can't assume absolute continuity with respect to each other. It's not really possible. So we are just keeping it very sharp. Second thing is the proof itself will go in a particular way where it is more amenable to the IPM thing because you're taking difference between two quantities. So these kinds of expressions are sort of more useful. That's why we go through IPM. Can you do a proof with some other divergence? Probably it's possible. I'm not saying it's not possible, but this is very natural. It's just algebra. Yes.
So I exactly follow PV distance. So that's very clear. So and I'm just writing that out. Expectation P1 fx minus expectation under P2 fx is fx times P1x minus P2x.
So it's a subset definition of PV.
Yeah.
Yeah. So PV will work out. But I didn't understand the last part. Kernel functions.
I mean, if you use kernel functions, it defines a discrepancy measure. And that's called maximum mean discrepancy. And I have to go to Hilbert spaces to tell you what this discrepancy looks like. But the usual version is the expected value of kernel of x comma x, where x is sampled from P1, plus the expected value of x comma x, where x is sampled from P2, minus 2 times the expected value of kernel of x comma y, where x is sampled from P1 and y is sampled from P2. Basically, you take the self-kernel average of both minus 2 times the cross-kernel average of both. This defines a distance. Okay, you can show that this is exactly equal to soup over all functions in the RKHS space, which is induced by the kernel. For every positive definite kernel, there is an RKHS. We produce the kernel Hilbert space. So if you take functions in that Hilbert space and you do the expected value of both, but I did absolute value. I think there you need to worry about something else called Hilbert norm. So the norm is actually very different. So the discrepancy between these two functions in the RKHS space under the Hilbert norm, that would exactly be equal to this. You can either compute it like this, or you can actually search over RKHS space and then try to match them. Okay, this is computable. The other kernel function, it takes order n squared to compute.
And in fact, that is a generalization of the other.
There's no generalization. It's just I change function classes. If I change my function class to that of an RKHS space that is induced by a kernel, you will get this distance function, and this is exactly equal to the Hilbert norm of this. Right? If I do just absolute value where f is limited to Lipschitz functions, you'll get Wasserstein distance. Absolute value, f is a classifier, you get total range. Okay. Yes.
In the architecture, are you ensuring that pi is 1, 1? Like, there's some constraint on pi there, so that it's 1, 1.
So the proof requires 1, 1. In this, what would you do? You do what you do, which is just have. Yeah, but there are recent neural architectures that are invertible. Basically, people have thought about what's called invertible flows. So if you look at it, there's a systematic way of constructing neural nets, which are actually end-to-end invertible. So the one-to-one-ness is sort of guaranteed, right? You could use them, and that's one way. And there's a lot of literature on how to actually reduce assumptions on the bijection property that they usually have, because we only need one-to-one. We don't need on. So yeah, so there are multiple works. Maybe you can adopt one of those neural nets. What they do in their paper, I don't think they can.
It's a black box.
It's a black box. How would you? So that's why the open problem is very important, right? The open problem is very important because I said I didn't tell you that phi has to be one-to-one. I only asked what are the phi such that this is true. So maybe there's some other principle from which you can actually obtain phi, and you can still prove that it is equal. But in practice, yes, it is a bit difficult to constrain one-to-one. In which case you have to constrain your neural nets a little bit. But there are classes of neural nets that have some invertibility property. I don't know of that space that well, but there are invertible.
And here you're probably jumping ahead, but the space of P you will search for will sort of like educate the calligraphic F you'll use for that.
Correct. No. So F is something very different. F will act on any space.
No, that's fine, but I'm saying that the IPM that we use here, what is the calligraphic F that is used for? Or like what?
I mean, it depends on what you can implement. Usually, you can implement MMD, or you can implement Wasserstein.
Oh, so the point is that you can work with multiple Fs. That too is a separate black box.
That's a separate black box. This is how GANs, discriminators in GANs are trained. So what you do is you first choose a phi, then you basically do an optimization in the other direction to gradient ascent over the function class. What function class can you do gradient ascent over neural net? So most likely you'll go for the Lipschitz criteria. If you can parameterize other spaces, then you can do optimization over them also. I'm not saying you cannot, right? So then you fix a F, then you move your P and your H's in the other direction. That's how training proceeds. But I'm not going into the detail of how it is trained. It's all in the paper. Is there any questions?
It's just a black box. If you give me some bounds on these regrets, what you'll prove is just.
That's all I prove. So I'm not going to go and argue that a very specific training procedure is going to converge anywhere. So that's not what I'm trying to claim. If you give me a final phi and a H and something that satisfies the IPM bounds, I'm just going to relate the counterfactual error to factual error because that's what I'm interested in. Because counterfactual, presumably you don't see. So you want to estimate, you want to relate the error to this error. That's what I'm. Is it clear? Yes.
Is there some equivalence between some of these metrics? Like, can I bound what to see in terms of
KL to TV is there, that's correct.
So KL to TV is Pinker's, but that only will work if both of them are absolutely continuous with respect to each other. For total variation distance, nevertheless, this definition you can define without any of that also. Wasserstein and total variation distance, they don't go well together. The reason is that, so the dual of this is actually a coupling with the transport cost, and it's a continuous transport cost. Okay, so it's just L2, actually. It's not L2 square, but L2. Now, I can make some small change in your nth decimal digit, even for your single 1D function, and create such a huge difference that, so for example, all my mass is on variables where the 10th decimal digit is always even in your base 10 expansion. And for the other distribution, it's always odd. Total variation distance is 1. You can perfectly distribute it because it's just completely, you can draw a separator. All you have to do is just look at the digit and just draw a separator. But Wasserstein distance is arbitrarily small because instead of the 10th, if I go to the 100th decimal place, the Wasserstein distance will just go to 0. Right? So there are worst case distributions. So I can hide the difference where the distance is small, but total variation distance is a classifier. It only worries about whether I can pass a line or not. It doesn't care about which line you're passing. Right? So generally these two, this is very strict. This is a bit weak in this sense. I'm not claiming that Wasserstein is weak in general. What I'm trying to merely claim here is that total variation distance is a very sharp thing. Any small discrimination that I can do by passing an arbitrary classifier, I will be able to do it. So the witness function is very powerful. Wasserstein witness function only Lipschitz functions. So if your main difference is in some 10th decimal place, clearly your function can't suddenly output two numbers which are very different because it's Lipschitz. So your witness functions are contained. Therefore, this distance function is weak. Okay, as to MMD, it's a very different ball game. I'm sure there are relationships, but I don't have anything on top of my head. This essentially is dense in all the L2 functions, right? So it has some power, but it's only limited power. But one thing I can tell you, if the MMD is non-zero, then the distributions are not the same, almost sure. Which means there is a non-null set in the sigma algebra over which the probabilities are different, right? So in a strong sense, in the limit, MMD sort of recovers the same thing as the total variation distance, assuming you have a characteristic curve. But finite samples, it depends. Like you always estimate total variation distance by using a classifier and hope it goes to the base of the classifier or something like that, right? So here what you do is just take a kernel and you just evaluate that expectation. But in order to evaluate that expectation, it's not very easy to do it, right? You need a lot of samples before it can converge. So finite samples, I don't know what is better, but what I'm trying to say is that between these two, this is certainly weaker. Between these two, I wouldn't say one is weaker because for characteristic kernels, if it is non-zero, the distributions are different, which means total variation distance will be also very weak.
Yeah. Can I find, so this is a question that's probably unrelated to today's topic, but can I always find kernels such that 3 will recover TV? The kernels is strictly more powerful because it's bivariate, and therefore, like
this is a different space altogether. This is a classifier. Its output is only 0, 1. This is real functions, like they output real numbers, but it's just that it's an L2, meaning it's square integrable functions, but it's dense in square integrable functions. So you can find RKHS spaces which are dense in square integrable functions. Therefore, they can really distinguish between any two distributions. Right? Gaussian kernel is one of them. But the only thing is the number of samples you require by the time you actually approximate this is extraordinarily huge because of the sharp tail. Now I'm going more into kernel theory. That's not my motivation. I just wanted to say that these are different ways in which you can compute distance. Are there any other questions?
TV is almost always the most distinguished.
Yes.
Upper bound.
Pretty much it. Okay, so let me actually grab the proof. Write the proof. The only problem with the proof is that I just have to define a lot of notation. Okay, so it's very clear that I'm not going to reach instrumental variables today. But let me try. Okay, so let me write some quick things. Okay.
Stop in with the interview.
Okay, so let me actually define some errors so that it contextualizes what I'm actually even trying to prove. Okay. So, yeah. So you have learned the H and the P. Okay, so the training is all done. Somebody gave you H and P, right? And I know that for just concreteness, I'm going to assume mass sustained distance. Okay, so the mass sustained one between P of X, P is equal to 0, comma P of X, T is equal to 1. Let's say, yeah, this is some mass sustained distance. Okay. Now, let's consider y1. So there is a y1 for every x. Only that whether you see it or not is the only question. So there's a y1 for every x, right? So there's a joint distribution. So now what I'm going to do is I'm going to take your loss function, it's least squares, let's say, and I'm going to take your target, which is yt, I'll use yt, and h of p of x, comma t. This is my estimate, right? H0, depending on whether it is t is equal to 0. H1, if it's t is equal to 1, I'm operating on p of x. So this is my final estimator. I'm going to estimate yt. Okay. Now I just integrate with respect to the potential outcome conditioned on a specific person x. Okay, it's a conditional estimate. Okay. Let's call this some L of yt. Let's just call this L of yt. Okay. Now there is no treatment, no factual things here. There's x, there's counterfactuals. There's always a conditional distribution. It's just that I don't know what it is. I may not be able to know, but these laws can be defined. Okay. Okay. Now I'm going to define two losses. It might be a bit confusing. Okay. Is yeah. Okay, so for convenience, let me just call it L of t comma h comma p. Okay, because those are the main parameters over here. So I fix a small t and x. I basically define this distribution. So this is integral. This loss per point. You can only take a factual distribution, which means people who are treated or untreated, but correspondingly, this loss will be calculated with respect to only those counterfactuals. The cross things are not allowed. For the treated people, you are not estimating the potential outcome for t equal to 0. For untreated, you are not estimating t is equal to, y0, sorry, y1, basically. But only the match you are estimating by this loss. That's why it's called the factual loss. Okay. Now, this is nothing but the probability of t is equal to 1 times the factual loss for t is equal to 0 plus 1 minus probability of t is equal to 1. The factual loss for t is equal to 1. So t is equal to, so this is t is equal to 1, this t is equal to 0, where I'm just splitting based on the two distributions. Okay, which is p of, so p t is equal to 0 of x is nothing but p of x given t is equal to. And p equal to 1. The only difference in this definition is that instead of integrating with respect to the joint distribution, I integrate with respect to the conditional distribution with respect to t is equal. That's the only thing. And the p of t comes out. right? So this is just integrated with respect to dp equal to 0 of x. This is integrated with respect, sorry, is equal to 1 of x. This is pt. Okay, these are all definitions, nothing abstract so far. Okay, now let's define what is called the counterfactual loss. Erase this, unfortunately. Okay. So the counterfactual loss, instead of t, I have 1 minus t. Okay. Basically, if you're treated, I'm going to penalize you on whether you are estimating the untreated potential outcome. If you are untreated, I'm going to actually penalize you based on whether you can estimate the treated potential outcome. Okay. So this is the counterfactual loss. This is nothing but integral, the same L, right? The only question is what is the distribution you're using? Here I'm using density function, p of x comma 1 minus t dx dt. By the way, people who are not familiar with d mu, it's just density times dx dt. You just write it dp, but this is just a measure. Here I'm explicitly writing the density function. If you're not comfortable, all you need to change here is small p of x comma t dt dx dt. Okay. So here what I'm trying to do is I'm looking at what is the probability of 1 minus t, but I'm penalizing yt's like estimation error. Okay, this is not computable, right? Because for those people, I don't have yt, right? But it can be defined. Okay, so now that everything is defined, now let's go to the estimate. I mean, what quantity am I estimating? I'm actually trying to estimate the expected value of y1 minus y0 conditioned on x. This is what I'm trying to estimate. There is an estimator that is simply h of p of x comma 1 minus h of p of x comma 0. Right? So the error that I care about in the individual treatment effect is actually nothing but the expected value of tau of x minus tau hat of x. This is what I want toบอก.
The actual error for t equal to 0 and t equal to 1, you're taking the integral of L with respect to the t equal to 1, which is the conditional distribution of x given t equal to 1.
Yes. Times, yes, correct. Times p of t equal. This is all the error in the factual data. When you did regression, you take all errors together, that will be the C. I'm further decomposing it as error for the first group plus error times the second group times the probability in which the first and second group are correct, right? That's all there is. There's nothing complicated. Okay. Now I define this. Just take it from me that epsilon CF is also equal to the probability of t is equal to 1 times epsilon t is equal to 0, the counterfactual error, plus 1 minus probability of t is equal to 1 times epsilon CF t is equal to 1. An analogous definition. Here, what is epsilon CF t is equal to 0? You are actually trying to find out for the treated people, what's the error on estimating the y0 potential outcome. The treated people. Okay, so just to be concrete, I'll expand that epsilon CF. It's just a definition. There is really nothing like complicated I'm saying yet. Yeah. So epsilon CF t is equal to 1 is nothing but your loss function with respect to 1 comma h comma p, but integrated with respect to the distribution p of x comma 0, which is p t is equal to 0 of x dx. This is epsilon t is equal to. That is why it is multiplied by the probability t is equal to 0. Okay, that's why the total, this is a conditional distribution and then you multiply. Okay, so the error is calculated with respect to the unknown quantity, and then you are actually averaging with respect to the opposite of whatever that you are doing. Right. Similarly, t is equal to 0, you can write. Is it clear or it's confusing?
Could you repeat the explanation for the counterfactual error? What is the px comma 1 minus the first line? L px 1 minus the first integral.
This integral?
No, the one to the left of it.
This one.
That's a definition.
No, that what is that integral?
This integral?
Yeah, what is that?
You just take the density when so you take first of all treatment is equal to 1. Okay, which means you ask what is the joint distribution of x comma 0, but then you calculate the loss with respect to 1. It's basically a mixture of these two quantities. So that's what I was about to write next. So this epsilon CF is just nothing but probability of t is equal to 1 times this guy plus 1 minus probability of t is equal to 1 times the other one. So basically there are 4 loss functions. Same, different. That's all.
Even in the infinite sample, you cannot estimate.
You cannot estimate this. You don't even observe it.
But
Under ignorability, you are going to do.
each X, you will get both treatment and non-treatment.
No, for the same individual, you either treat that person or not treat that person. If you are lucky, if the same features exist in 2 people who have been treated and non-treated, you are lucky.
Yeah.
But we are not counting on anything else.
Positivity is there, but
Positivity and ignorability is equivalent to doing regression in the infinite sample limit. That's all I'm said so. But this is about finite error, like given h and p, I am actually calculating the generalization.
just to like the regression or the shapes that you learn, it is it's only for the in the architecture, the TarNet architecture, the point was for X's which were treated, you would run the top half of the regression, and for those that were not treated. But here, when you apply the definition, you do ignore that.
This definition cannot be computed, but I do exactly the flip of it.
Okay.
Ideally, I want to relate this to something factual. So this is factual.
Okay.
Same. Right? This is computable. This is not computable. I'm going to argue that this is nothing but some version of this plus IPM. That's going to be the proof.
In a sense, what you're saying is I learned this regressor, which has like this 1 or 0 as an extra input. And for the counterfactual, so I use my H to generate.
But under ignorability only. Otherwise, you can't go through certain things. Is it clear? Yes.
Sorry, the second line on the left side of the board. So you're integrate for each point x. So you're not integrating over x. What is the integral over? Second line on the left side.
This is integration over yt, the potential outcome as a distribution.
So yeah, just to
No, conditional distribution. Yt given x. I'm integrating with respect to the density function of the conditional distribution given x dx. Sorry, dy.
at each point x, right? So
At each point, this is a function of x. Here I'm integrating over x in all the other.
oh, you're integrating over all outcomes. I thought there are only 2 outcomes.
No, yt is a potential outcome. Could be any scalar variable. Could be binary also. Yes.
If I was integrating over phi of x of x, so then this epsilon cf t equal to 1 will be equal to epsilon f t equal to 1 with some.
So 1-to-1 functions, d phi x will be equal to.
Yeah. So 1-to-1 function.
But p of phi of x will be different from p P of 5 of x given t equal to 0 will be different.
It's people.
So like these two, then they like epsilon CF t equal to 1. When I'm integrating with respect to phi of x will be close to epsilon f t equal to 1. If I was integrating with respect to phi of.
That is what I think the derivation will entail.
I'm not yet integrated with respect to phi of x here. I'm going to do a chain of it. For now, everything is dx. Right? Okay. Okay, the first proof, which I think is the most important one, I'll prove it. Then I'll just claim the other one, which involves ignorability, which you guys have seen already for 4 lectures. But the most important thing is, how do you relate the counterfactual error to the factual error? That's the main thing I want to actually go to, right? I mean, it's a bit obvious at this point, but let me actually do it more carefully. Okay, so here is the small trick. Note that here, probability of t is equal to 1 was combined with a factual error when you are trying to estimate y1. But in the counterfactual, I have flipped it. It was actually doing probability of t is equal to 1 was combined with when you're trying to estimate potential outcome y0, right? So you sort of need to maintain that structure. So we are just going to do that. So the proof actually will say the following. The final proof, I have to erase this unfortunately.
If P of x comma t was equal to P of x comma 1 minus t, this is a randomized control trial, then they both right.
Correct.
And you will do change of variable just to.
Yes, just to get this. But when they are different, I need to bring in the integral property matrix on that. So it's not something very complicated. It's just a very simple observation. Okay, so just to recall, there was epsilon f t is equal to 0. Then there is epsilon f t is equal to 1. Right? This is the error in the untreated group, is the error in the treated group. That's it. Very simple. Yeah. So this is estimable. We know this. The only thing that is not estimable is this. You agree. So now what we are going to prove is that this is actually less than or equal to. Okay, I will be very careful with the use. That's why I opened the thing. Yeah. So 1 minus the probability of t is equal to 1 times epsilon f t is equal to 0 plus the probability t is equal to 1 times P1 epsilon f t is equal to 0 plus the IPM between P t is equal to 0 of 5 and P t is equal to 1 of 5. Maybe there's another factor which is basically the Lipschitz constant. And I'll come to the Lipschitz constant later. I have to make one more assumption about this, so let's call it B5. And I'll come to this, what this means. Okay, this is what I want to prove. Okay, this basically relates something I can't compute with something I can actually compute plus the IPM. That you guys agree, right? Okay. Now, so note that I have already written in a non-consonant manner. Right? This is the right answer is not epsilon because this is untreated, treated. This is treated, untreated. So they are mismatched intentionally. Okay? Because this was mismatched intentionally to start with. So all I have to now prove is that epsilon CF of t is equal to 1 minus epsilon f of t is equal to 1 times 1 minus probability of t is equal to 1 plus probability of t is equal to 1 times epsilon CF of t is equal to 0 minus epsilon f of t is equal to 0 is basically upper bounded by some constant times the IPM. This is all I need to prove. Okay. So all this is just less than or equal to 1. So you can just bump them off. The only thing is I just need to prove that this is upper bounded by the IPM times some constant. So I'm just going to argue that it's not now that it's here. It's not very complicated. Okay. 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 So I'm going to cheat a little bit. So epsilon CF t is equal to 1 minus epsilon CF t is equal epsilon f t is equal to 1. They are actually nothing but integral. Again, I'll remind you, L is always evaluated with respect to HP and 1, but integrated with respect to a different thing. But here you integrate with respect to the same thing. The functions are the same, the distributions are different. Okay. This is exactly where the integral probability metric actually came from. But I have to do a change of variables. I'll do a change of variables. So there is okay. So change of variables has two things. So one is x is actually given by xi of r, or r is given by phi of x. So these two are the transforming variables. I'm going to go from x to xi, right? So dx is nothing but the Jacobian with respect to xi r with respect to r dr. Okay. Now, if you do this thing for the probability density functions, it's the opposite, right? So that is related as follows. I mean, this is a well-known result. Yeah. The probability distribution of the new transform variable is nothing but the old one times the Jacobian. This is also known, right? So if I go from this to here, dpx will be dpr divided by the Jacobian. Dx is again j, the Jacobian times dr. They actually cancel each other, right? So let me show you very carefully. So this is L of h r comma 1 times. So I have to go from p of t is equal to 1 of x dx minus the same thing, p of t is equal to 0 of x dx. Right? Now I know that px is given by pr divided by the Jacobian. But dx is nothing but Jacobian times dr. Right? So this is transformation rule. You can go and check it yourself. This is random variable time. Yeah. So 1-to-1 as I'm using here. Right? So essentially the thing is you get this Jacobian cancelled, right? So you actually get integral of L of h comma r comma 1 multiplied by dp t is equal to 0 of r minus dp is equal to 1 of r. Okay. Now I'm going to assume that phi was in such a way that this function is basically Lipschitz. I mean, I have to make some assumption, so I'm making that assumption over here. Okay. So with respect to phi, this function is actually Lipschitz in r. So what you will actually get is L times the Wasserstein 1 of Pt is equal to 0 of r, comma P is equal to 1. Okay, here I cheated because I just assumed some very complicated laws to be Lipschitz. Okay, but that's an assumption that you have to make. It will have some Lipschitz constant, and whatever that Lipschitz constant is, will basically multiply the Wasserstein. So here there's really no magic that is really happening. The main magic happened when I considered these expressions on the right hand side already. Okay, so I have basically related the counterfactual loss to the distance between the two distributions. Any questions? Yes.
So
This is the witness function, by the way. L is the witness function. And it's a function of R.
what I wanted to say is the Jacobian does not appear. Is the Jacobian bounded by L times I here?
No, the Jacobian has to exist though, yes. It has to be, the determinant has to be positive. That's why it's a one-to-one function.
And also it's
So one-to-one function, so the Jacobian will exist.
derivative continuous. Absolutely.
Yes, yeah, so I have to assume that the first derivative is continuous and all that, yes. The assumption is very clear, but yes, the first derivatives have to be continuous. First partial derivatives have to be. So one-to-one first partial derivatives have to be continuous, yes, all that will go in here. All the nice assumptions that will make sure that the Jacobian will exist, right? And then you have, yes.
Just asking if L appeared because of Lipschitz constant appeared from the Jacobian.
No, not because of Jacobian, because of this. Because of the loss function. All I'm saying is this some loss function which is Lipschitz. Right? By the way, this loss function anymore doesn't have P in it. It already has only R and H in it. So it's least squares. So least squares. So if the inside thing is Lipschitz for a bounded domain, this is going to be Lipschitz. But I am assuming that the loss function is Lipschitz.
And there is B.
Yes, it's B. There's
That's why like the persistent one is the right metric to put.
I mean, actually, the general definition is L divided by B phi is in some function class.
Okay.
And whatever the function class is, you can define IPM with respect to that. There's nothing complicated going on over here. Okay. So I've related the counterfactual loss to the factual loss. Yet related the ITE to this, right? That still remains. I will only state the result because time is up. And I would like to at least mention some a more interesting thing about potential outcomes, which is instrumental variables. Unfortunately, I've relegated to the last 10 minutes. It's a very fascinating topic by itself. So I just state the other theorem. So here, all I've said is if you have a matching bound, the counterfactual loss can be related to the factual loss if you know that the L function is some Lipschitz function for it. That's all we have found. Okay. Now, the way the proof proceeds further is to show.
Interestingly, it's just like you need an IPM that is able to address the loss function.
Right.
So as long as you're able to pull that off, it's sort of so it's not like you don't have to worry about all one yet. You can be even more conservative.
Correct. You can be even more.
The IPM function needs to be Lipschitz and pi.
It just has to take the IPM only was used at exactly at the last step. Till that point, it's all integral. So now I tell you that the two measures are close such that this integral is small. You're done.
But like I'm just trying to understand IPM, the role of pi in deciding my function class comes from it being Lipschitz in pi of x.
Yeah, this is a very complicated condition. You have to be Lipschitz in phi of x. AMH. So that I don't know. I mean, it's just an assumption that they make, but for the IPM metric, if it is something else, you have to assume that that lies in whatever that space is. So it's not for all loss functions. So that is true. It is not for all functions.
Right. Also, it's not very transparent as to how you would think. I'm looking at it now from a more use case or like a data science thing. The idea would be that you learn this file through the TarNets thing.
Correct.
But it's not obvious. It's not like this expression does not give you like anything close to a closed form expression. It says you keep doing it till the loss is low and you will. Black box.
Yeah, black box. There's nothing. So the only novelty is that if you have the IPM, you can relate to distributions closed. Any function, imaginary or otherwise, you can always integrate and then find the difference, and you can bound the difference. Because one of the integrals is not observable. So this is totally not observable at all. But I know it's the same function. So I can actually get rid of it. That's all it is saying. It's not saying something very transformational here. Okay. Now there's another part of the proof where you actually relate the error that I started with, which was the IT error, to these factual things. I am not going to go into that because that's just more manipulations of variance and conditional means and so on. So I'll just state that here. Okay.
Nice thing is that this is certified in the sense that,
Correct.
as you're saying, that once I have a good C, I can certify it.
That is true. So now what you can prove is that the IT error, which was the expected value of tau hat of x minus tau of x squared, right? This is nothing but epsilon CF plus 2 times epsilon. There's another factor, but I mean, you can even have a tighter bond, but that's not very important. So you have this function. So it can be related to the counterfactual error and the and this error. And you can actually show that counterfactual error can be upper bounded by 2 times the factual errors plus IPM. So essentially, all you will get is a bunch of factual errors plus IPM. Okay. Here you actually use ignorability and all that. You need to track what you're estimating, what you're not estimating, right? But the most important part is where does the IPM actually occur, which is relating the counterfactual error and the. See, for any function that you try to estimate, you don't have one distribution, you have another distribution. But if you know that they are very close in IPM and this function is Lipschitz, clearly it is L times 1. That's all I've said. Is this clear? It won't work without one-to-one. It's a very important part of the transformation. If it's not one-to-one, I have no idea what happens.
You can take away is nice, right? The architecture does speak to a method of doing things.
Method of doing. You match, you have X, preserve ignorability, you do regression, you're fine. Now the question is how you get to ignorability from ab initio. That's a secondary problem. We have never discussed so far in 4 lectures. That motivates the Perlian models.
But if you assume ignorability,
Yes.
then this is a good architect, like meta.
Yes, you have. Sorry. There's a question.
So the matching you needed to estimate the error,
Yes.
not to estimate the dependence.
No.
Just needed to
Estimate the error. The finite samples, all I'm saying is for any H in phi, I know that the counterfactual error is the factual error, which I can compute. I'm not claiming it will go down. I'm only saying that whatever that error is, it is whatever it is, plus the error. So you would rather, try to minimize all of that. I mean, always minimize upper bounds in neural, in machine learning. So you just optimize. It just motivates that.
It's not just an upper, it's saying that, look, I want a transformation and I want to learn a regression over transformation. The transformation should be such that not only is the regression good, but it also brings the distributions together.
Correct.
That and also is a very useful insight to me. It's not obvious.
Right. So you got the distribution together.
So like
it improves the so it doesn't improve the estimation error itself.
No.
It doesn't improve the estimation error.
But no. But the counterfactual error, which you can never estimate, is related to the factual error plus the stuff.
Right.
But that's what you care about.
Right. But that is in how much do you? It all comes down to how much do we trust in our estimate.
Correct. Yeah. I'm not giving you any technique to minimize the factual error. Okay?
No, but the point is important. Like, if you look at the TarNet thing, and let's say you remove this IPM part, right? So before the lecture, if you would told me, that would have been my guess. You pick a P and find a regressor that minimizes the error with respect to P. The point is, if you do that, you have no bound. You have no bound for this epsilon CF. So adding this second layer now gives me a bound.
You have no bound for it.
The epsilon CF is completely off the rails. You have no control over it. If you do not bring this IPM box into it.
So it's like saying, right, like if I have training data and you're assuming the test is also going to come from the same distribution, but you have not seen any test sample, you would like to bound the generalization error. So in that limited problem,
It's not. The relation comes only in terms of the IP. Like you could have learned a fee, which has a very good classifier, but imagine now that the IPM was huge. It is possible that epsilon CF is epsilon F plus this huge number. I mean, it's an upper bound, I know, but it gives you a bound which you did not have at all to go. It's not, what I'm saying is it's not merely an analytic addition. It also has practical.
all we are saying is that if the factual error is low, which you can always obtain by regression, that does not imply the counterfactual error will be low. As long as you bring both of them together, then I can assure you that it's certainly okay, it's upper bound. That's all we are saying.
So we are using it to bound epsilon CA.
Correct.
And we can bound it by epsilon.
That's all.
But error will always be epsilon CF plus epsilon.
Yes, and that is again some function of epsilon plus IPM.
Right. So it's like I'm building an estimator. Now, if you didn't care about it, is the best estimator. You don't really care about what error it produces, you are well and good. You don't need to go and find it. Now you want to know how good my estimator is doing. Then I need to go and find a few. That will give me a trust saying, oh, my estimator is actually good because of that. Now I'm being able to relate epsilon to epsilon. Because epsilon F is something as epsilon
CF I cannot think of.
I cannot.
I actually think it's a bit more nuanced. So maybe you should.
Yeah. So yes.
I would pose it as a constraint optimization setting where the error, IP error is a constraint. Rather than a regularized.
No, that is what I told you, right? Like the regression error plus another regression error plus the IBM is what they optimize. They literally do that.
That is one version of the problem. So the other version of the problem is the constraint optimization. So that is regression error 1 plus minimize regression error 1 plus regression error 2 such that this is less than epsilon.
This is less than epsilon. The only problem there is how are you going to solve the constraint problem? No, right? I mean, this is all like continuous distributions, functions, spaces.
It's just one more on that side.
Yeah.
Maybe an alternate.
I mean, we have no idea what this constant is too. All you can do in practice is just put lambda over there. That's all you can do. I mean, whether it will actually achieve it or not, we have no idea.
There is no assumption on the tau. Like was there any assumption on tau as function of x?
Tau is always a function of x, right? Because
like, is it ellipses or something? Because how did you relate tau to epsilon?
Okay. So here, if you look at the loss function, it had yt and h of phi. Let's say that's least squares. Now you can write this as conditional mean plus the errors. But that error will be variance. But that you can bound away. This will be the error in the means, which is what you're actually looking for. Right? And once you have those two things separated, then you can actually relate it to epsilon f and epsilon. That's how the proof goes.
Don't need an assumption on tau.
Yeah. There is no assumption on Lipschitzness of tau or anything else. Yes.
Is there any merit in thinking that the IPM is sort of a regularizer on?
Correct. Matching is a regularizer. That's all they have said. But durability. If you have durability, you match, you do whatever you want. You can do regression estimates, but the point is that your true thing might be so far off and you will actually get this. Right? That's a separate matter. Okay. Is it clear? Okay. Now, okay, this should not have been relegated to the end of the talk because it does disservice to all the people who worked on it. I'm a big fan of this instrumental variables estimation. In economics, there are two, I wouldn't say just two, there are many methods proposed for potential outcomes. I mean, all the things that I've said, including. But what if ignorability is not satisfied? What can you do? Can you ever come up with something for which ignorability is definitely not satisfied? Okay, it's a very complicated problem, because without ignorability, none of what I've said till now actually holds. So you have to go back to your drawing board, right? It turns out there's this one case where you can do something very remarkable, and it has been put to use in economics time and again for many years. It's one of the cornerstone methods in classical economics. It's called instrumental variable regression. So I just want to introduce you guys to what that thing is and what is the estimator. I would have liked to go to the proof, but probably I'll skip it, and I'll ask you guys to read Herman's book, so that next lecture at least I can start with the Persian stuff, right? But this is very important, because in practice, let's say I'm trying to conduct a randomized control trial. What can I do? I can only give you the tablet. Whether you will take it or not is not under my control. So there is only intention to treat. There is never natural treatment that anybody can force on a person. Okay. So essentially, all you can randomize is the intention to treat. You can never randomize the treatment. This is a very simple observation, which means you are actually in this case. So let me actually go there. So I only take 5 minutes. I know I've exceeded time by 10 minutes. I'll just take 5 more minutes, because it's a pretty interesting thing. Unfortunately, I've delegated it to.
Raj, quality audience. Take them.
Yes. So this is called the IV method, instrumental variable method. So the idea is the following. So you have a treatment T, you have an unobserved variable U, and you have Y. So this is unobserved. Okay. Clearly, this is not satisfying ignorability, or you can test it if you want. There's no X, but the potential outcome should be independent of T. It's not, because even if I cut off this thing, there is a backdoor path. I mean, we'll come to backdoors and all that, but this is an informal way of saying that ignorability is just not satisfied here. Okay. Now, there is what is called an instrument, C, which is the intention to treat. Like, I am randomizing and giving you the tablet. Whether you will take it or not is not under my control, right? So T could be based on many other things. Maybe you saw the news, you thought, okay, maybe this tablet is not something for me. I don't want to take it, right? So you can do all of that, right? But it is not only for this particular case. Let's say you are interested in understanding whether some alcohol intake could impact something, right? I can't force someone to take alcohol or not take like that. So what I can always find is some other variable that acts like an instrument. It is like an intention to treat, but some other actual physical variable. Maybe some genetic thing that has got to do with your alcoholic metabolism, which basically means whether you took alcohol or not, the rate at which the alcohol gets ingested in your body, right, might be controlled by some other factor, and that could, analyzing that could actually tell you a lot about the effect that you're trying to estimate. Okay, and there are many more examples in economics throughout where people hunt for what is called an instrument. But what does an instrument have to satisfy? The instrument has to satisfy the following conditions. Z and T has to be correlated. I mean, this is obvious because the intention to treat and the treatment has to have some correlation. Right? Otherwise, it's a problem. The second one is that Z and Y don't have any more common causes. Is that Z, if at all it has an effect on Y, it's only through A. Only through T. Only through T. Okay. This is called the endogeneity condition. Okay. Essentially, Z is somewhat like a variable which affects Y only through T, but it doesn't have Z and Y themselves are not confounded in any particular way. Okay, there are potential outcome statements you can write for each one of these. I'm not going to write that now. But the more interesting part is that there's some more extra conditions you require. They're called homogeneity conditions. I'm not going to write that because I just want to introduce very shortly and just finish it. Maybe next lecture I'll take it up. But under all these four conditions, there's a very beautiful estimator for the treatment effect of T on Y, and which is what I want to actually tell. Right? The estimator is so the average treatment effect. This is not individual treatment effect. Let's go back to the original problem. The average treatment effect. Clearly, it's a confounded problem. There's really nothing you can do here. If Z was not available. If Z was available, satisfying all these three conditions, then what you can show is that the average treatment effect is nothing but you first regress Y on Z is equal to 1 and Z is equal to 0. Okay. Then you divide by, you regress the treatment on the intention to treat. Okay. Intuitively, if all the people are very obedient people, denominator is 1. Right? Because if I asked you to treat, you took the tablet. If I didn't ask you to take, you didn't borrow it from someone else. You still didn't take the tablet. Right? So this is 1, and this is the normal estimator. Okay, so this is basically saying Z almost is like T, although it's not directly correlated with Y in any way because it was randomized. Therefore, it's as though I can actually directly estimate the effect from Z to Y. Right? But when there is disagreement, or they have a term for it, which is basically non-compliance, then this term actually starts becoming very, very important. But what's important is that if this is non-compliant, which means there is noise in this arrow, the effect between Y and Z also does not reflect T very well, which means you need to sort of boost it up. And the amount by which you boost it up is basically related to the amount of non-compliance that you have. These are English stories, but you can actually formally make a thing out of it. And what is very interesting is that this can also be realized in what is famously called a two-stage regression. For two-stage OLS, two-stage regression, and so on. So what you do is you first estimate the expected value of T given Z. Okay, we'll call it F of Z. Then what you do is you actually regress Y on B0 plus B1 times F of Z. Okay, and the regression coefficient B0 would actually give you the 8 effect essentially. Okay, so this is another way of looking at the same expression. You first estimate this, and then you try to regress here. So what you now do is Y1 minus Y0 will be essentially B0 plus B1 times the difference. So B1 is actually the thing that you want, and you can take it to the denominator, and you can actually see that this can be realized in in a two-stage regression. So you first try to estimate the treatment, then the estimator can be used as a deconfounder, although there is a confounder there. Why? Because this T's estimate, it depends on some independent random variable. Therefore, this noise is not same as this particular. It's a bit different, right? So that's the intuition. Under these three conditions plus some other homogeneity conditions, I'm not telling you what it is. This estimator actually is consistent, or rather, this is the correct 8 effect. Now, suppose I don't have this fourth condition. A lot of people have derived upper and lower bounds on the average treatment effect, which is better than the non-trivial bounds. Okay, and I think there are lots of interesting open problems as to what type of conditions give rise to what type of tighter bounds, and when can you actually do this 8 estimation or some other estimation. Okay, but this is a very beautiful thing because the thing is completely confounded. But because the intention to treat is not confounded with Y, you are actually using the fact that Z cannot affect Y except through T. And if there is a non-compliance, essentially this is noisy. So you're just controlling for the noise in the stage. So that's the interpretation. But we want that this condition 4 is parametric. It's very important to state that because I don't want you to think that this can be solved non-parametrically. Okay, so that's a mistake a lot of people make. So there's a very clear paper by Balke and Pearl in 1998, which shows that if you only assume some version of 1, 2, and 3, you can give bounds, which are non-trivial. But if you further assume make a parametric assumption about this, then this estimator is actually consistent. Okay. And a lot of people got very near Nobel Prizes for using this in various places. So it's a very, very important tool. The most important thing is I don't have to worry about the magnitude of U, the entropy of U, sensitivity of the treatment with respect to U. I don't have to worry about any of that, right? So that's why this instrument of variables is actually very good for that. Yes.
So sorry, I didn't catch the fourth assumption. So that's question 1. And question 2 is in the denominator, I include the treatment. But if I know the treatment, then I not directly check the.
No, but T and Y are confounded, right? So ignorability is not true. The regressions won't help you.
So I cannot perform interventions where.
No, you don't have any. You have only observational data. So I gave you some intended to treat you in some way. You either took it or you didn't comply. But depending on some unobserved factors that also affect the outcome. So if I don't have Z, there's no way of estimating this from observational data. It's not unique. But the point is the fact that you have an instrumental variable automatically makes this an estimable number. In some cases.
Like T and Y are like ignorability. Let's say X is empty here. The X that we were.
Yes, X is empty.
Yeah. So is Z and Y ignorable? No.
Z and Y have to be ignorable. Because if there is a confounded, you at least need to know them.
Okay.
That's a conditional version. If you don't know them, there should be nothing. That is very important. Z and Y don't have common causes.
Starts acting as like a meta ignorable with respect.
True, but I am not interested in the effect between Z and Y. I am still interested in the effect between T and Y. I'm not changing the problem. But you are telling me, oh, I have some other variable that's not ignorable with Y. Okay, I'm computing AT. Sure, you can do that. But that's not what I'm interested in, right? I'm interested in this. And still you can do that as long as you can find the amount of disagreement over it. Because this is literally what you would do for effect estimation of Z on Y. You're right. But that's not what I want. I still want the treatment effect, but you can do that. Basically, that's the key. Yes.
So the first condition, wherein B being correlated is not enough, that should cause T.
Okay, no, it's not true. So, okay. You're already going into the political regime. You can have this instrument, same thing holds. You can subset equal to 1. So you take two variables, you create a new variable, but you condition on the is equal to some particular S. You only take those examples. That forms the observation data. So you end up correlating these two. So it's fine. Any of these three will work.
This correlation. So an arrow from T to Z.
From what?
T to Z.
T to Z. No, but there has to be an effect to Y. Otherwise, it will not.
Is T to Z, then I have found.
Because this will be 0, right?
In collider case also, how is there an effect from?
Because you condition on S equal to 1, so there is a correlation effect actually. So the main point is that this conditional distribution have to be non-zero. I mean, this difference has to be non-zero. In what you said, yes, there is correlation, but if you actually look at Y given Z, there is really no path basically. So that will not work.
So if there's T to Z arrow, second point is not there.
Yeah. So you need to have an effect on Y through Z in some sense. I mean, I'm not giving you the potential outcome version of this. That's why you're not able to verify. But if I gave you the potential outcome version of all of this, then it will become very clear what our models are about. In that, I think the T to Z model will not be.
So 8 is effectively like estimate of the intervention.
Yes, but you're intervening here, not here.
Correct. And we're estimating that directly by observational data.
Yes, and this is the estimator.
And that's very nice.
Yeah, that's what I'm trying to say. Yeah. So it's a very non-trivial fact. It's not so simple.
And can you not like do that for all people who claim intervention is necessary?
See, the problem is the conditions you require, right? So first of all, usually these three are the main conditions that are basically set to identify instrumental variables. For linear models, these three are enough. The fourth one is a slightly, if you want to go to non-parametric, then there is some assumption that you need to make. Only under that assumption with Z and T to be binary, everything, you can actually write this formula. So there are lots of conditions over and top of three, but the three actually identifies what an instrument is. But whether you can estimate it perfectly or not depends on some parametric assumptions. Okay. So the exact condition is the expected value. So the potential outcome of A comma Z is equal to potential outcome of A comma Z prime. This is equal to the potential outcome of A. In the do calculus, you intervene on A and Z, you intervene on A, but then set Z prime to be something else. It's same as YA. Right? This is the kind of condition. Right? That's what 3 is about. And if it's satisfied, whatever model that satisfies it, I think that's totally fine. I don't think there's any other problem.
Next case Y, T.
Z and Y don't have common causes. I think this is just simply the expected value of YA. I think all this says is that YA is actually independent of Z.
You say YA, you mean YT.
Sorry, YT. This is true. Okay. Yeah, so whether you treated somebody, whether you intended to treat somebody or not, if that person was given this, there's only some effect. Basically, your intention to treating is not like going to affect the outcome in any complicated way. That's what this is saying, right? This is just the anti-correlated. Okay. Plus the more parametric assumptions you need, under which you can actually show that this is actually the experiment. Yes.
So that YT Z that equality. That is the thing that intervening on T and Z together is same as this intervening on T.
On Y, the effect on Y, yes.
Effect on Y.
Yes.
So then that is
that is also possible. Yes, true.
Like from T to Z.
The reason I'm a little bit uncomfortable is that so far, other than Y, there has never been a descendant of the treatment. And you are basically asking me to consider a case where there is one. And that's like some sort of an off-track thing. So I'm a little bit like, I just want to go and think about all these other conditions to make sure that it's satisfied. That's why I didn't say yes. Right? Yeah. If it was pre-treatment, everything is fine.
Thinking about it as graphs or
good. So at least you came to that point. So the whole point of teaching potential outcomes for the last 4 things is that 2 things should be very clear to you. Ignorability is a very central linchpin on which the whole thing rests. So the question you might ask is, first of all, it's an untestable condition. When can it hold? At least intuitively. The second thing is when it doesn't hold, some magic seems to be happening here. And I'm able to explain that using graphs and all that. But if I have to express everything, I have to express using conditions on counterfactuals, which I'm never going to see. Right? These are very strong conditions, which you are never going to be able to verify. So the question is there an ab initio generative model from which you don't specify any counterfactuals? They are sort of implied by the model. And then the moment I look at the model, I'm able to conclude what I can do, what I cannot do. And that's exactly what the Perlian promise is. But there's a more deeper issue there. It's not just to solve this problem, although the motivation traditionally has been this. It's to explain what ignorability is. It's to explain something else. But it goes very far. I mean, my personal opinion, having worked on that, is that it goes a bit farther than just that. And I'll come to that next lecture because already I'm half an hour late. I was supposed to introduce that, but yes. Thanks. Yeah, and